Hi everyone, I'm Codenatics, and this is a tutorial on depth first search. So, firstly, let's go over. You might have encountered some problems, which you might have been confused on how to solve them. And now we'll go over one such example. So, this is a tricky problem unless you know depth first search. Keifa decided to celebrate his first big salary by going to the restaurant. He lives by an unusual park. The park is a rooted tree consisting of n vertices, with the root at vertex 1. Vertex 1 also contains Keifa's house. Unfortunately for our hero, the park also contains cats. Keifa has already found out what are the vertices with cats in them. The leaf vertices of the park contain restaurants, but Keifa wants to choose a restaurant where he will go. But unfortunately, he is very afraid of cats. So there is no way he will go to a restaurant if the path from the restaurant to his house contains more than n consecutive vertices with cats. Your task is to help count the number of restaurants where he can go. So you guys can pause the video now and go to this link right here. You'll want to go to this link right here and see if you can solve it. This link will also be in the description below. So if you have taken an attempt at it and you're stuck, then you probably want to continue watching. So before we can actually dive into this problem, there's a couple of background things we have to cover so that we can understand exactly what this is asking. So what are graphs, that is, in programming? A graph is a pictorial representation of a set of objects where some pairs of objects are connected by links. The interconnected objects are represented by points termed as vertices, and the links that connect the vertices are called as edges. So we're just going to create just one small modification to this quote is that we are going to also refer to vertices as nodes. So let's take a look at an example of a graph. Here you can see that 1 is a node, 2 is a node, 3 is a node, 4 is a node, and 5 is also a node. Now the lines that connect them are edges. So now that we have covered the basics of a graph, we can start talking about acyclic versus cyclic graphs. A cyclic graph is a directed graph which contains a path from at least one node back to itself. An acyclic graph is a directed graph which contains absolutely no cycle, that is, no node can be traversed back to itself. So just quickly to debrief what this means, basically there are two types of graphs. So there is a graph which in this type of graph you can draw cycles through the graph. So you can start at one node and you can go through a cycle and end up back at the same node. So here, let's draw an example of a cyclic graph, and then we'll look at an example of a acyclic graph. So here what we can do is we can just take, so let's start a graph like this. So this can be our first node, then we can have a second node, a third node, and finally a fourth node. So what we can do is we can take a point, draw it like this, and we can just draw edges the same way we did earlier. Except now you can see that if I start here, I can travel here, and then back. And so what this means is I can do a cycle to come back here. Now in an acyclic graph, we just saw one, which was this, 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 and this. In an acyclic graph, you can't do that. If you observe, here there is no possible way for you to do a cycle. If you go here, you can't go back because you can't go back the same way you came. You can't go back, you can't cross the same edge. And that's just a rule of graphs, is that you can't cross the same edge twice. So then you can go here, and then you go here, but that didn't work. So you try and go this way, but then there's nowhere to go. So you're stuck. There's no way for you to do it. So that's basically acyclic versus cyclic graphs in a nutshell. So acyclic graphs are also known as trees. A connected graph with n vertices and n-1 edges cannot have any cycles. There's a mathematical proof for it, and is then necessarily a tree. So if you take a look back here at our example right here, you'll notice in this there are 5 nodes, and there are also 4 edges. So there is one more node than there are edges, which means it's a tree. Right, so similarly, a graph with n vertices and n or more edges has to have a cycle and is necessarily then a cyclic graph. So this should make a little bit of sense to you. And one of the main reasons why I said connected graph is because that just means any vertices can reach any other vertice. So in this, you'll notice in both of these graphs, the top one is cyclic, the bottom one is not. You can reach any vertice by going from any other vertice. So why is it called a tree? Well, this is the graph that we have been using so far as an acyclic graph. What if we rearranged it like this? You'll notice the graph is still the same. The shape of the graph doesn't really matter. All that matters is that 1 and 2 are connected, 2 and 4 are connected, 2 and 3 are connected, and 3 and 5 are connected. So you'll notice this graph and this graph are the same. In fact, this animation clearly shows how they are the same. But now it looks much more like a tree. In fact, we can rearrange this even further to look like what you would popularly see as a Christmas tree or something like that. So this is one of the major reasons why we call it trees. So let's talk about rooted versus unrooted trees. Rooted trees have one root, many children, well, not many children, you can have some amount of children, and leaves. The root is the start of the tree. So going back to this example right here, the node numbered 1 would be the root. The node numbered 2 and 3 would be children, and 4 and 5 would be leaves. Now let's explain all 3 of these in a little more detail. So the node 1 is the root, and the root can be picked from anywhere. Usually the root is called as 1. But whenever there's a root, you can think of that as the start of the tree. It's the highest point in the tree. Now all other points are then going to be children or leaves. So how do you know what's a child, and what's a leaf? Well, a leaf is something at the end of a traversal. So what do I mean by this? Well, if you take a look right here, this node 4 is at the end of the graph. There's nowhere else for you to go from 4. Similarly, 5 is also a leaf. There's nowhere else for you to go from 5. So any node that satisfies the property that there are nothing adjacent to it that's below it, you can think of those as leaves. And children are the ones that aren't roots, but they also aren't leaves. In other words, the children have parents, and they also have children of their own. So, for example, 2 is a child. Its parent is 1. Its children are 3 and 4. 4 also happens to be a leaf. So you would say the children of 2 are 4 and 3, and 4 is a leaf. Now, 3 also happens to be a child. This is because it has a parent of 2 and a child of 5. 5 also happens to be a node. But because 5 also happens to be a leaf. But because 3 is not a leaf, we know that it has to be a child. Because it's not a root, it's not a leaf, it has to be a child. And so 3's parents is 2, its child is 5, 5 is a leaf. So unrooted trees have no roots, no children, and no leaves. The graph can start from anywhere and the order does not matter. So for example, this is an unrooted tree. Now you can think of this as an unrooted tree. If you'll observe, these two graphs are actually identical. It's just the way we have oriented them and made them look. This one right here on the screen looks more to be unrooted than this one, which looks to have a root at 1. However, both of these are the same graphs. So rooted graphs are usually directional in that you can only travel down the tree. Unrooted graphs are usually not directional. You can travel any way. Now this is key. The usually is key. You can find instances of when you will use a rooted graph that is not directional. So just quickly to clarify, directional means you can only travel in one direction. So for this one, you can travel in any direction. You can travel from 2 to 1 or 2 to 3 or 2 to 4, or you can travel from 4 to 2, or you can travel from 1 to 2. However, in this graph, it's clear you travel from 1 to 2 and not backwards. So unrooted graphs can easily be turned into rooted graphs and vice versa. As we just saw, those two graphs are identical. However, the way that we drew them, oriented them, and thought about them changed whether they were rooted or unrooted. So finally, we can move on to depth first search. So depth first search is a traversal algorithm, which, as the name suggests, traverses a graph. Typically, it's a rooted graph to search for something. So the depth first search means that it's going to go as deep into the graph as possible, and then it's going to backtrack, and then go deep, and backtrack, and then go deep. If it doesn't make sense, it's okay. We're going to be talking about this a little more in detail. Not all depth first search implementations search for something. Sometimes they just traverse the graph. And to shorten the words depth first search, we will commonly refer to it as a DFS algorithm or a DFS implementation. In a DFS algorithm, the program traverses on one branch of the tree all the way to the bottom of the tree, and that will be all the way to a leaf node. At that point, it recurses back up to the most recent splitting point and goes in the other direction. It continues this way for the whole graph. So let's go back to this example that we have been continuously using. Let's say we have a computer. That computer, and this is the computer processor which is going to run this algorithm. So the computer is going to start here at 1. So in a depth first search algorithm, the first thing it's going to do is go to 2. So we have visited 1 and now we're going to 2. Now it's going to go to 4. Now you'll notice 1 was a root, 2 was a child, but now 4 is a leaf. So it's hit 4, it's hit a leaf, there's nowhere else for it to go. So it's going to backtrack up to 2 and look, is there another way for me to go? And the answer is yes, there is. The computer can go to 3. So it's going to go to 3. Then finally it's going to go to 5. Now it's at the end. Ideally, what a computer is going to do is backtrack up to 3, to 2, and then to 1. And so once it does that, it's finished. It's back to 1. There's nothing else it can do, so it's going to stop. And so the path that it's followed here is it's gone, and I'm not going to count the double counting where it's going from 1 to 2 to 4, and then it's going back to 2 because it's recursing back upwards. So it's going to be 1, 2, 4, 3, 5, and then it's going to stop. So that's the order in which a depth first search algorithm would run on this simple graph. Before we can start actually coding it, we need to understand what we need for this. The first thing we need is an adjacency list. This will keep track of the nodes adjacent to each node. This is usually a 2D array, and in Java, it's an array list array. So here, in this graph example, we can say that 1 and 2 are connected, 2 and 3 are connected, 2 and 4 are connected, and 3 and 5 are connected. So, over here, what we can say is if we create our little list, we'll say, I'm going to keep a list. So let me use a little better color. So I'm going to keep a list right here. Give me 1 second. So in the first slot, if you'll notice, we have 1 is connected to 2. So I'm going to keep another list here, which is going to say 2. Then in the second slot here, we're going to see 2 is connected to 1, 3, and 4. So 2 is going to be connecting to 1, 3, 4. Then in the third slot right here, we see that 3 is going to be connected to 2 and 5. So if 3 is connected to 2 and 5, we just write that down. 4 is connected to 2, and 5 is connected to 3. And so this is going to be our sample adjacency list. So pause the video now and make sure that you understand why this is the adjacency list. So just taking a look back here at the graph, we see 1 is connected to 2, and then 2 is connected to 1, 3, and 4, and then 3 is connected to 2 and 5, 4 is connected to 2, and 5 is connected to 3. So the next thing that we're going to need is a visited list. This is the list that is going to keep track of which nodes have already been visited. So in this example right here, by marking these nodes as green, we kept track of which nodes we had visited. If we didn't do that, well, let's work out actually what would happen if we didn't mark those nodes as green. So going back here, we'll try it out. So we've got our graph here, 1, 2, 3, 4, 5, and I'll just draw little connectors between these. So first, we would start out here at 1. We're going to start right here at 1. And then we're at 1, so the algorithm, it's going to try to move from 1 to 2, because for 1, the next adjacency one is 2. Then at 2, it's going to look, what are its adjacency lists? Well, in its adjacency list, we've got 1, we've got 4, and we've got 3. So it's going to take the first one that it sees, which is 1, and it's going to go to 1, node 1. Now it's back at node 1. So at node 1, it's going to check its adjacency list. In its adjacency list, there is 2. So it's going to go to node 2. Now it's going to check node 2's adjacency list. For node 2, in the adjacency list for node 2, there is node 1. So it's going to go to node 1. And you can see it's just going to bounce back and forth between these two and not get anywhere. Now what a visited list does is it leaves this marker here. It leaves a marker here that says, hey, I visited node 1. Don't come back to node 1. So now it's going to go to node 2, and it's going to say, okay, what are my nodes in node 2? I have node 1, node 3, and node 4. But wait, node 1 is visited. I should not go there. So then it's going to go to node 3, and then it's going to go to node 5 from there. It checked node 2, but node 2 is already visited. Now node 5 is over. So you might be thinking, okay, well then where will it go? Won't it be stuck? It won't reach here? So the way depth research is no. it's going to actually recurse back. The computer isn't going to move from here to here. It's going to recurse back into this and into this, and then it's going to move to the next spot. So the next 1 and 2 is 4. So the computer is actually going to move jump right down to 4, because it'll recurse back here, and see, okay, now I have to go to 4. And finally, it'll recurse back up in here, and then up into here, and then it's done. And that's actually it. It's hit this first node again. There's nothing else adjacent to the first node. This is going to recurse back into the main program, and we're done. And so in this one, we would get 1, 2, 3, 5, 4. And you might be wondering, why didn't we get 1, 2, 3, 4, 5? 1, 2, 4, 3, 5. And that's simply because we just, instead of choosing to go this way, we chose to go this way. Right? So now we are finally ready to code our first depth-first search program. So here I have just an empty class, and we're going to start off by creating our main category, our main function. And in most programs, you would be using this for competitive programming. You would need to take an input, but for the time being, I'm not going to take an input. I'm just going to directly say and create my adjacency list. So we're going to use the example that we had right here. We're going to use this example, and we're going to create a depth first search algorithm on this. So step 1 is to create a public static array list of integers array, and we're going to call this adjacency. Second step is to create a public static Boolean array called visited. Now here, what we're going to now want to do is we're going to want to initialize the array list. So we're going to want to say we're going to say adj is new array list array of size 5. For us, it's going to be 5 because we have 5 nodes. And we're going to want to iterate through here for I in range 5 and say adj of I is equal to new array list. And this will create a new array list for each slot in the array list of integers. Now make sure that you don't do this. You don't want to do arrays.fill adj new array list. This is actually going to fill each of them with the same array list. So whenever you edit any adjacency, it's going to edit all the other adjacencies. So you want to do it like this. Next, you want to say visited is new Boolean array of size 5. Visited will automatically default to filling with falses. And just to show that, we can print out arrays dot to string of visited. But that's not really what we want. Now that we've filled all of these, we actually need to fill out our adjacency list. So we need to say adjacency list of 0 dot add, and we need to, according to this PowerPoint, we need to add 2. Except we have to be careful here. Remember, our adjacency list and visited lists are 0 indexed. So if the node is 1, in their computers, this node will actually be the 0th node, right? And if our node is 2, in our computer, this node is actually going to be our first node. So let's be sure to be careful about that. And we're going to say .add 1. Next, the adjacency of 1 .add 0. Adjacency of 1 .add 2. Adjacency of 1 .add 3. And then adjacency of 2, this is going to be our third node, dot add 4. This is going to be our fifth node. Adjacency of 3 dot add, we're going to want to add 1. And finally, adjacency of 4 dot add 3, I believe. No, dot add 2. So now we've got our adjacency list set up. Now let's get to work on creating a depth first search function. So in the PowerPoints, I hinted constantly by saying it's going to recurse backwards. It's going to use recursion. Now, actually what's going to happen is we're going to use function recursion in depth first search. So what we want to do is create a function, public static void DFS. This is going to take in an integer node. Step 1 is to create visited of node is equal to true. Then we're going to want to print out the node, and this will just tell us what route we're taking. Now we're going to want to iterate through, so for int next in adjacency of node, if not visited of node of next, DFS of next. And that's it. That's actually all the DFS is. And then we're going to want to DFS on 0. So this is going to iterate through each one, and it's just going to simply depth first search through. Make sure you understand why this is the same thing as what we worked through. It's going to start at the first node. It's going to set the visited of the node to true. It's going to print out the node. Then it's going to take the next nodes in the adjacency list. If the node is not visited, it's going to depth first search through that node. So now we can run this program. Java C, and then we want to compile it. And after it finishes compiling, we're going to want to run it, so df. And so, as you can see, firstly, we printed out our visited array right here, and it initialized to full falses. So we can comment that out. Now, it starts at 0. It went to 0, 1, 2, 4, 3. I'm going to add a +1 here just so that it's a little more clear to us so that we can understand the path that it took. It started at node 1, went to node 2, went to node 3, went to node 5, and then finally finished at node 4. And so that's a basic depth first search algorithm right there. Now, of course, you can pass in more nodes. So, just as an example, I'm going to create a public static int array depth. And we're going to initialize this to be depth is new int array of size 5. And so what I'm going to say is I'm going to start this off with int node and then also int depth. And not int depth, I'm going to say int d. So we're going to say visitor of node is equal to true. D of node is equal to, depth of node is equal to d. And then we're going to DFS with the next and then d plus 1. So what this is going to do, and finally we just have to create a 0 and then arrays dot to string of our depth. So what this is going to do is it's going to take a depth and it's going to set its depth to that. It's going to set the depth of the node to the depth it got in. For each next adjacency, it's going to give each one a new depth of d plus 1, which is going to say that for each adjacent node that's not already been visited, that node is going to be considered as one level deeper. And so then we can compile, and you'll see 0 has depth of 0, 1 has depth of 1, 3 and 4 have depths of 2 and 2, and 5 has a depth of 3. Now, quickly, we can go back to our example over here. And over here, you can see that this is actually true. Node 1 has a depth of 0, node 2 has a depth of 1, nodes 4 and 3 have depths of 2, and node 5 has a depth of 3. Now, just to be a little more clear again for us, I'm going to say that node 1 actually has a depth of 1. In which case, I've changed it right here. We can recompile, and you'll see it works just the same. We have 1, 2, 3, 3, 4. So, let's go back to the program. Let's go back to the problem right here. So Kefut decided to celebrate his first big salary by going to the restaurant. And we have read this problem already. But now, armed with the knowledge of depth first search, you should be able to calculate this. Of course, you're going to need a little extra things. The first thing you're going to need is anytime there are no more adjacencies next to it, then you've got to understand that that's a leaf node, and you've got to check whether or not there are m consecutive vertices there. M consecutive cats. Oh, wait a minute. Consecutive. Sorry. If it contains more than m consecutive cats. So the first thing you need to do is you need to keep the track of those number of cats, and you need to check if the number of consecutive cats is more than m, you need to stop. So what you can do is you can keep track through the inputs and parameters. And what I mean by that is, if we take a look over here, remember how I put this depth in here? Instead of that, you can say int consecutive, for example. And then each time a node has a cat, you could say the depth, the consecutive, is going to increase by 1. Now, if there are more than m consecutive cats, then you know that that leaf is going to be bad, and you need to stop there. Now, if you ever encounter a place where there is no cat, the criteria that there are m consecutive cats means that you need to stop. Means that you need to reset the number of consecutive cats, because now it's going to be 0. So try and figure out the rest of the logic for this on your own. It is still difficult, but depth first search definitely makes it a lot more easy. And just some quick things to remember. Our lists are 0 indexed, so make sure to subtract 1 from each node that's given as an input. You can return out of the DFS immediately if the number of cats exceeds m. Keep track of that visited list, or you will hit an infinite loop. Don't forget what the problem is asking. And make sure that your adjacency list, visited list, and the value of m is public as public static variables. Make your DFS function static, and make the adjacency go both ways, and that if A is adjacent to B, then B is adjacent to A. If you are stuck, feel free to reach out to me in the comment section. I will be uploading a walkthrough for this problem to this channel very soon, so make sure to subscribe and turn on the notifications to never miss another video, and to be notified immediately when I release that walkthrough. So if you did enjoy, please do like, and if you really enjoyed it, please do subscribe. It helps me out a ton, and I will see you guys in another video.